Welcome to Lesson 4 of the Sandhill Soaring Club Ground School. This lesson is about glider instrumentation. So part of controlling a glider is that you need to take in a lot of information about what the glider is doing and what the air around the glider is doing. Most of that information you will get by looking out the window and listening and the feel of the controls, but you also have instruments available that'll provide you information. The instruments all have little characteristics that they're not always telling you exactly what you want to know. So you need to understand how the instruments work so that you can understand what they really are telling you. So in this lesson, I'm going to go through several different types of instruments that you'll find in gliders, starting with the pedostatic instruments. Sometimes these are called air data instruments. Next, we'll talk about the magnetic compass, then the inclinometer and the yaw string, pretty simple instruments, the gyroscopic instruments, some of the avionics that we have on gliders, which some have, and then finally we're going to do another session on aeronautical decision making. And in this session, I'll introduce the PAVE acronym. So the pedostatic system is about sensing pressures. There's a couple of different types of pressure that need to be sensed in order to make the right calculations. One type is static pressure. Static pressure is basically what the pressure would be if you measured it from something that wasn't moving and the air wasn't disturbed by a glider flying through it. So the challenge in measuring that, of course, is that you're measuring it from a glider that is flying through the air. So to measure it, there are static ports on the glider, and they're strategically located in places where the pressure against the glider tends to be pretty much equal to the static pressure. It isn't necessarily exactly equal to what the static pressure is, but it's the best we can do when we're in a moving glider. The most common place you'll find them is on the sides of the fuselage, kind of behind the wing area. These need to be checked during pre-flight to make sure there isn't something covering them up. The other sensor is a pitot tube. The pitot tube is trying to measure the pressure of air as if it was moving along at the same speed as a glider and then was brought to a stop, which would be a higher pressure. That's called the total pressure. So common places to see a pitot tube, the most common place on a glider is on a little stick sticking out from the front of the tail. Sometimes you'll see a pitot tube at the nose of a glider. Unfortunately, that's also a place you like to put a tow hook, so that's why the tail is more common. On aircraft with engines, sometimes you'll see the pitot tube out on a wing so that it's away from the propeller blast. So the altimeter utilizes the static pressure. It does not use the pitot pressure. And it uses this to estimate altitude. It does that by taking that pressure measurement and based on a standard relationship between altitude and pressure, it indicates what altitude would be associated with the pressure that it's measuring. Of course, altitude is not the only thing that influences air pressure. Um, air pressure is also influenced by weather systems. There are areas of high pressure and low pressure you'll see on a weather map. So to correct for this, there is a setting for the altimeter where you indicate the local barometric pressure for the area that you're flying in. Typically, that's the airfield that you took off from. If you're doing cross country, you may have to make adjustments to that as you move from place to place. This can be set either by obtaining this information from a weather source, or just turning this dial while you're on the ground at a known altitude to make the altimeter read the correct altitude for the place you're taking off from. So there's different terminology we use for altitude. Indicated altitude is just straight off whatever your altimeter says. Pressure altitude it's actually a way of expressing pressure. It's the altitude when you enter in a standard barometric pressure into the altimeter, it will read pressure altitude. That's used at very high altitudes, so that the aircraft that are flying long distances don't have to make such frequent changes to their barometric pressure indicator in their altimeter. True altitude is your actual vertical distance above sea level. If you put the correct thing in your altimeter for your local barometric pressure, your indicated altitude and your true altitude should be very close together. Indicated altitude has some possible instrumentation error, but they're very close. So density altitude isn't really an altitude at all. It is a indication of air density. It's expressed in terms of altitude, so it's the altitude at which the air in a standard atmosphere would have the density that you are currently experiencing. Density is very important for a lot of types of performance calculations. So knowing the density altitude helps you if you're looking up performance numbers where the performance number changes with altitude. You should use your current density altitude when you look up in those tables. Absolute altitude refers to vertical distance above the ground as opposed to above sea level. So this is what we care about when we want to know how high we are above the airport, because we want to get in a traffic pattern at the correct altitude. Absolute altitude is what we should be thinking about. So the next pitot-static instrument is the airspeed indicator. Airspeed indicator uses both the pitot pressure and the static pressure. In fact, what it really looks at is the difference between the two. So the difference between the two is something called dynamic pressure. The formula for that is 1/2 times the density times the velocity squared. So what it's really directly sensing is this dynamic pressure, but it's converting that to units of airspeed by assuming a standard sea level air density. The stall speed, the approach speed, the minimum sink speed, the best LO or D speed. These are all speeds that you will be interested in setting your airspeed relative to. They fluctuate with air density in exactly the same way as the airspeed indicator does, so that using indicated airspeeds is the correct thing to compare to. You will tend to stall at the same speed, the same indicated airspeed as density changes. Some of these speeds get indicated on the airspeed indicator itself by these colored bands. The green arc is sort of the normal operating range. So the bottom of the green arc is stall speed. And stall speed does vary with weight a little bit. So it's usually the place that's marked on the airspeed indicator is the stall speed at your maximum weight. So when you're flying at less than maximum weight, you may notice that the airspeed indicator goes a little lower than that before you feel the aircraft stall. The top of that green arc and the bottom of the yellow arc is something called the maximum structural cruise speed. So in still air, it's safe to fly in the yellow arc. In bumpy air, being in the yellow arc can be problematic, and you want to stay down in the green arc. And then there's a never exceed speed is indicated by this red bar on the airspeed indicator. And that is the speed, even in perfectly still air, you should not go above that speed. In aircraft that have flaps, you may see a white arc that indicates the range of speeds at which you can have the flaps deployed. Just like we did for altitude, speed also we have different terminology. So indicated airspeed is exactly what it sounds like. It's what your airspeed indicator reads. Calibrated airspeed is correcting the indicated airspeed for instrument errors or installation errors. And when we were talking about the pitot and the static port there, sometimes it's impossible to put them in a place where they will exactly sense what they're intended to sense. So you can, by doing some flight testing, determine what those errors are and have ways to correct for them. But generally those errors are small enough that we don't need to do a lot of correcting for airspeed indicator errors. True airspeed is an actual measurement of how fast you're moving relative to the air that you're flying through. You can calculate the true airspeed based on your indicated airspeed, your temperature, and the pressure. The temperature and the pressure are what indicate your actual air density, and air density is what causes the difference between your true airspeed and your indicated airspeed. Your ground speed is a measure of how fast you are moving relative to the ground. So it's basically your true airspeed corrected for wind effects. And of course, we care about that for several reasons. If we're trying to get someplace, ground speed is what's going to determine how long it takes us to get there. And ground speed also affects how long it's going to take to get stopped when we do a landing. The last of the pitot-static instruments is a variometer, and that measures the rate of change of pressure to determine whether you're climbing or descending. It's a quite precise measurement compared to the vertical speed indicator that you'll find in most powered airplanes. It's a little more precise in sailplanes. But it isn't a perfect measure. There's a little bit of a delay. The what is telling you at a given moment is usually what your climb or sink speed was a few seconds earlier. And a feature that is common in variometers is something called a total energy probe, which is used instead of a static pressure to compensate for something called stick thermals. And by stick thermals, we're referring to the tendency that when you pull back on the stick and you're slowing up, the glider will climb. And sometimes you're doing that subconsciously and you think you're getting a climb, but really you were just causing it with the stick. And when a lot of times you are intentionally changing speed when you think you're near thermals. So it's nice to compensate for that effect. And the total energy probe accomplishes that by sensing a pressure that it's not the pure static pressure, it's varied from that a little bit by a portion of the pitot pressure. It's not a perfect compensation. It still will show some, stick thermals will still show up on the variometer to some extent, but it helps make them less. So now moving on to magnetic compass. We have this because we want to know what direction we're going. So we're kind of fortunate when we fly around Richmond Field because around Richmond Field we've got lots of north-south roads and east-west roads, and a lot of the boundaries between farm fields run east-west or north-south. So you can pick your direction relatively easy by looking out the window at landmarks. A lot of places around the country are not like South Michigan where you can do that. So when you're flying in other parts of the country where the landmarks don't mark the north-south and east-west so well, magnetic compass is our primary way of knowing which direction we're going. So the magnetic compass determines your orientation relative to the Earth's magnetic field. So one problem with that is magnetic north is not necessarily aligned with true north. The North Pole, magnetic North Pole isn't at the same location as the true geometric North Pole for the Earth. The difference between the true north and the magnetic north is called magnetic variation. You can find the value for magnetic variation on the sectional chart because it varies from place to place. Near Richmond Field, the magnetic variation is 7 degrees west. So what that means is if you are pointed due north, then your compass will say 353 degrees instead of saying 360 degrees. Other places, the magnetic variation can be a lot bigger than that. Compass is also influenced by magnetic components in the aircraft. So that difference is called magnetic deviation, and you correct for that by looking at a little card that's usually posted somewhere near the compass that tells you what direction you need to have on the compass for different directions that you want to actually be going. So that's it experimentally determined. The aircraft is pointed in different directions on a that are known, and then somebody sees what the compass reads and writes that down. A memory aid to remember that which one is magnetic variation and which one is magnetic deviation. You can think of magnetic variation varies from place to place around the Earth. Magnetic deviation is associated with the aircraft. So you can think that some aircraft are deviant and they want to take you other places. So another thing that happens with magnetic compasses, one problem with magnetic compasses is that they're not very stationary. They bounce around a lot. So if you get in a little turbulence, the compass is rotating back and forth, and it's kind of hard to see where it is at any given time. But a additional thing is that when you bank the aircraft, that can change what the compass reads. That's called a banking error. And it happens when you're on northerly headings or southerly headings. It doesn't happen when you're going straight east and straight west. The way to remember it is this NOSE acronym, NOSE, which stands for North Opposite, South Exaggerated. So when you're headed north and you bank to the left, your compass will show a turn to the right, the opposite direction. If you're headed south and you bank to the left, it will indicate a large turn to the left, even before your aircraft's actually started to point a different direction. So when you're headed east or west, it will read correctly, and then as you move through the turn, it will change. The another way to think of that is that when you're going north, the compass leads, and when you're going south, the compass lags. So when you're going north, you need to turn out or stop your turn quite a bit before you get to the desired heading. A similar type of compass error is from acceleration or deceleration, and that works a little bit the opposite way. It happens when you're headed east or west, and if you accelerate, that when you're headed east or west, your compass will turn to the north. If you decelerate, it will turn to the south or indicate a turn to the south. So the way to remember that pattern is ANDS, ANDS. So when you're making turns by your compass, you have to kind of remember these things. Fortunately, you're usually not accelerating and decelerating a lot while you're making turns. So the yaw string and the inclinometer are how we know whether we've got the airplane pointed in the same direction that it's moving. That's called coordinated flight. We want to fly coordinated most of the time. The yaw string is just a piece of string, literally, that is taped at the front edge to the canopy, and the air blows it in whatever direction the air is moving. So if the air is moving as it, straight over the aircraft, the yaw string will stick straight up. If you're kind of flying sideways through the air, then that air blows the string off to the side. The same information is available from the inclinometer, which is this ball in a little bit of an angled pattern here, so that when you're coordinated, the ball will sit right in the middle. If you're not coordinated, the ball will go off to the right or the left of the inclinometer. So if you're uncoordinated and you want to get coordinated again, you correct by pushing one of the rudders. And the saying is step on the ball. So if you're in this situation shown in this right picture, you would want to step on the right rudder because the ball is off on the right side. Or if you're looking at the yaw string, which is usually easier to do in a glider, step on the bottom of the string. So gyroscopic instruments our gliders in our training fleet at Sandhill don't have gyroscopic instruments in them. So you won't, what you're learning here, you won't see that when you get in the training gliders. The purpose of the gyroscopic instruments is to provide information about your orientation, all three dimensions. If for aircraft that do instrument flying, of course, that information is critical because you can't get that information by looking out the window when you're in a cloud. Also, at nighttime, it's hard to get that information. But in our gliders, we don't fly in clouds and we don't fly at night, so it's not as important. For visual flying, it basically we always get that information by looking out the window. If you do have gyros, you can get it a little bit more precise than what you can get by looking out the window. Your gyro will help you know whether you're in a 30-degree turn or bank or a 35-degree bank. So the artificial horizon is an instrument that it's intended to look like you're looking at the horizon looking forward. And it indicates your bank and your pitch. A directional gyro is giving you the same kind of information that you get from your magnetic compass. And the two instruments complement each other quite a bit. It doesn't have some of the types of errors that a compass has that we just talked about. It doesn't bounce around in turbulence and be hard to read. One problem it does have is that it tends to gradually drift off over time. So using the compass and a directional gyro together, you periodically, when everything is nice and stable, correct your directional gyro to be the same as your compass, and then use your directional gyro primarily, and then correct it again after a little while. A turn and bank indicator indicates your rate of turn. Not only just whether you're turning left or right, but how fast you're turning left or right. So radios are, some gliders have radios built in, other gliders do not. Our training gliders currently don't, although we're talking about changing that. We may If you listen to this at some point in the future, that may have changed. So built-in radios have some differences from radios you may be used to in other contexts. Typically, an aviation radio, the way you change from one frequency to another is a little different than other types of radios. They have an active frequency and a standby frequency. So the active frequency is what frequency you're currently listening on and talking on. And the standby frequency is another one that you've selected. So you have a knob where you change the frequency in the standby, you change the standby frequency, and then you push a button and that swaps the active and the standby frequencies. So to change to a different frequency, it's a two-step process. You turn the knob to set the standby frequency to the frequency you want, and then you push the button to swap them. That's real useful when you're flying through airspace where you need to be changing frequencies, because you can anticipate what frequency you're going to need in the future, put it in the standby frequency when you've got time available to do that, and then when it's necessary to make the change, it's just one button push to make the change. Another feature that some aviation radios have that you may not be familiar with from other types of radios is a squelch control. Squelch control is used to block weak signals and a lot of static that tends to come through the radio. So you set the squelch control basically to say how strong a signal needs to be before you want to hear it. So if you set it too low, you'll get a lot of static and a lot of irrelevant stuff that'll probably be hard to understand. If you set it too high, you can have transmissions that you wanted to hear get blocked. A lot of times then when there is a built-in radio in a glider, and most of our gliders that are two-place have front and rear cockpits, a lot of times the controls for it are only accessible from one of the two cockpits. In the case of the DG and the Club, it's the front cockpit. So something I recommend that glider students do in the course of your training is invest in a handheld radio. They're excellent to have when you are flying one of our training gliders that don't have a built-in radio. During the early parts of your training, you'll be with an instructor and they'll probably have one, but eventually you should have one of your own. And it's also just handy when you're around the airfield to be listening in on the frequency as you move around, retrieving gliders and things like that. So not all gliders have electrical systems. When they do, they use batteries as opposed to having, like a regular aircraft would have an engine-driven alternator or generator that provides the electrical power. In gliders, it's always based on batteries, and they need to be recharged. So during pre-flight of a glider with an electrical system, installing the battery is an important part of doing that pre-flight. And at the other end of the day, when you're putting the glider away, taking the battery out and putting it on the charger is an important part. That happens with the DG sometimes. We'll find that the previous people using the glider did not put the battery on the charger, so we don't actually have an electrical system that day. So there are a lot of times the amount of equipment that's installed in the glider, not everything needs to be working in order for the glider to be airworthy. Some of it is sort of optional, but we need to know which stuff is optional and which stuff is mandatory. So there's two different ways that gets determined. Some gliders, as part of their certification process, one of the pieces of information that was included in that certification is a list of what equipment needs to be operable in order for that aircraft to be airworthy. Other aircraft, there is no such list. So the standard list, when there is no aircraft specific list, is you need an airspeed indicator, you need an altimeter, you need a slip indicator, which can be a yaw string or a ball, and you need a magnetic compass. For motor gliders, there's some, the list is a little longer. There's some engine instruments that are required. And then as we'll get to in lesson 7, for some airspace that you might operate in that is, say, close to bigger airports, there's equipment that's required in order to operate in that airspace. We'll talk about that when we get to lesson 7. So what happens if something isn't functioning? So to be legally airworthy, when an instrument isn't functioning, the first step is that instrument required per the previous slide? So either on the, is it either listed on the minimum equipment list or on the standard list of required equipment? If it's listed there and it's not working, then the aircraft is not airworthy and you're done. If that equipment is optional, then it needs to either be removed or it needs to be placarded as inoperative. Basically you want it to be covered up so that somebody flying won't ever think that it's useful. Covering it up is the best way to make it known that it's inoperative. So before I get into the new material for aeronautical decision making, I want to review some of what we covered in the previous lesson. So we talked about how important making good decisions is before and during a flight. And aeronautical decision making comes down to formulating a good plan to begin with, and then updating your plan based on things that you detect during in-flight or in your preparation for the day's flight. We're always updating our plan. And in the previous lesson, we talked about the DECIDE model that was a way of making good aeronautical decisions. So there's a new acronym to introduce today, the PAVE acronym. And this describes different categories of factors that you should be considering when you're making your plan or updating your plan. The P stands for pilot. Anything you need to consider whether the pilot's in a good shape. And we'll discuss this in a lot of detail when we get into medical factors in a later lesson. A, the aircraft. We'll be discussing that a little more today. V stands for environment. Didn't want to use the E here because it would have made a funny acronym. So they used the V. We'll discuss, when we talk about weather, we'll talk more about environment and how that should affect your decision making. And the E stands for external pressures. So in the next couple slides, we'll talk about aircraft factors and external pressure factors and how they should influence your decision making. So I'm going to introduce a few scenarios here, and when we get together in person, I want to talk about, you know, how each of these scenarios would affect your decision making. So in the presentation, I'm just going to introduce them. You should think about them. When we get together in person, we'll talk about these and some others. So decision making is really easy some of the time. Like if you discover something that is clearly airworthy about your aircraft before takeoff, it isn't really very hard to make the decision that you shouldn't take off. The tough decisions are the ones that are more borderline. So let's talk about how some of these things would influence your planning. So let's say you get to the airfield and the aircraft that you're planning to fly recently had maintenance done. Maybe it was an annual inspection. Maybe there was something wrong with it that got repaired, but you learn that maintenance has been done and recently, and maybe the aircraft hasn't flown since that maintenance was done. Does that change your plan? What if you discover that the airworthiness certificate isn't in the pouch where it's supposed to be? So what if the aircraft that you're going to fly today isn't the one you usually fly and that you're used to flying? Some characteristics that could be different. It might have retractable gear and you're used to flying fixed gear. Maybe it has flaps, or maybe it has different types of instrumentation, like modern instrumentation called a glass cockpit, where information just gets presented differently. You can't say, well, I'm not going to fly because the aircraft's different, or you would never get a chance to use that aircraft. But how do you how does that factor combine with other factors when you're making decisions? So what if you're testing the spoilers and they work just like they're supposed to? They come up, they go down, they feel right, but there's a little squeak noise. They, and you didn't notice that noise last time. So let's talk about some situations where we have some equipment that we've determined to be inoperative. And as we went through a few slides ago, we've determined that the equipment is not legally required, but we still have to make the decision, should we be fine with the fact that the equipment isn't working, that something isn't right, or is this a situation where we should take advantage of our ability to just mark it as inoperative and continue on? So what if you're going for a solo flight today and you discover that the shoulder harness in the back seat is broken? Could say, I wasn't going to sit there anyway. Why does it matter? Does it matter? What if you're going for a flight in the DG and you discover that whoever flew it last time didn't put the battery on the charger? So anything that requires battery power isn't going to be working during your flight today. So you've taken off and maybe you're still on tow and you notice the yaw string doesn't move. Look a little closer and see, oh, when I shut the canopy, I shut the end of the yaw string in the canopy, so it can't move. What should I do about that? So suppose you're going on a dual instruction flight. You're going to go up with a flight instructor, and you notice that the airspeed indicator in the rear cockpit, somebody had marked it inoperative. But you've discovered it's not legally required to have two airspeed indicators. How should you change your plans based on that information? So you're in flight, and you notice that the airspeed indicator always says 55. That's that's the speed you wanted to be flying anyway, but you're normally not that steady. It doesn't seem to move when you do things that should change the airspeed. What should you do about that? Or you're flying an aircraft with a built-in radio and it's only reachable from the front seat. Maybe you were planning to take somebody for a ride today and you've had a rear seat checkout and you'd rather let them have the better view of being in the front seat. Does this matter? So the last topic we're going to cover today is the external pressures situation. So it's human nature to sometimes let things influence our decisions that really shouldn't be influencing our decisions. And the way to compensate for that is to avoid having them subconsciously influence our decisions by being conscious about it and taking note of the fact that some things are going on that could influence your decisions, and you want to be conscious about making sure that they don't. So what if you brought a friend with you today? Your friend's really excited about getting a glider ride today. How is that going to influence your decision making, and how do you make sure that it doesn't put improper influence on your decision making? Or it's October, maybe getting into November. It's the last chance you're going to be able to fly until April. Is that likely to change your decisions? So we're always making decisions when we're in flight about where we are relative to the airport and whether we need to be heading back to the airport in order to get in the traffic pattern, or whether we should stay out and continue looking for thermals. Would that decision making be any different if we were going for a silver endurance badge and we were really close to getting there?